Hi everyone, welcome back. In this lecture, I'm going to talk about Coulombs Law. Coulombs Law is effectively the amount of force between two charges during attraction and repulsion. So this lesson will be kind of into two parts here. The first part we'll talk about the mathematical way to model the push between two charges, and then we'll do more conceptual applications of it. Now the equation I'm going to show you is deceivingly simple. The way we'll treat it in our class is we're just going to plug and chug it. But in reality, when you have more than one charge, this is a vector problem because, as you can see from other, even just talking about charges, is that they push each other. So if they push at angles, then it changes the whole question. So I'll tell you we won't calculate this. However, you're very smart people. And I want you to be able to predict how things are pushed. Okay, so that's the last part of the lecture slide. So I'm just going to grab my, because it's all the way over here, my tablet, and I'm going to need a calculator for this. So get your calculator ready too. This lesson is important to follow calculation with me. You're probably like, I know how to use my calculator. Yes, you probably do. But I'm going to give you some tips and tricks on how to use it so you get the right answers, because sometimes if you don't enter it correctly into your calculator, you can make errors. Especially now I want to make sure that you're doing everything correctly. I'm going to move back and have some space here. Here we go. Some space. Okay, I kind of talked about this, but we're going to describe Coulombs law, do some calculations, and then model it with force diagrams. Okay. I know we skipped gravity, but let's pretend we didn't. So if we talked about gravitational attraction, the force of gravity, another way to calculate it, we have Fg is mg, which is true, but a different way to calculate the force of gravity is between the two masses, because masses affect the pull between of the pull of gravity. So the only time we really see or feel the effects of gravity is when one of the objects is really big, like the Earth. So in other words, if I put the Earth here and me, then I'll have a substantial force. If I put me and another person, not a substantial force. That's because this capital G here, called the gravitational constant, is very small. And gravitation is based on distance. Well, turns out that Coulomb's law is very similar. With gravitation, you have interaction of mass, and with charges, with electric force, you have interaction of charges. So actually the model that we use for it is actually very similar. So Coulomb's law in words is the force between the two objects. It's how much they repel and attract. And it depends on how much charge they have and how far apart they are. So here is the official equation. So Fe, so E can either be lowercase or capital. It doesn't actually matter, but it does refer to the electric force. Force is measured in newtons. It's not here, so let's write it in now. You know that force is in newtons, but let's write it to be complete here. So the force electric is actually I call it the electric force. It's the force due to charges measured in newtons. K is a constant, so you can actually program this into your calculator if you remember how to do that. You can do 8.99 positive ninth, then press the store button and then press alpha K, and you can program this number because this number is always the same. It's our constant here. Q1 and Q2 are the value of the charges in coulombs, and R stands for the distance apart. Now the distance is squared, so in fact the further away you go, the lower the force, and it goes in orders of squares. So, if I'm, if we look at force and distance, if I'm twice the distance away, then I'm 4 times weaker, because first of all, I'm 4 times weaker because 2 times, if I square this, 2 squared, I distribute the square, so it's 4d squared, first of all. And second, this is on the bottom of my fraction, so that's why it's inverse like this.
So if I am 3d away, then I'm 1/9 the force. In other words, my force is getting weaker. And if I'm 4 times the distance away, I am 1/16 f, etc. like that. So this will keep going and going and going and all that fun stuff. So, in fact, if you graph it, it's an inverse square graph, which just looks like this, which essentially means that the force is super weak. When far away. Far away. Like that. Sorry. Okay, another very important thing about all of this too is that these have to be in the right units. That they're not in microcoulombs, it has to be in regular coulombs, and that this distance has to be in regular meters and not in like centimeters or or micro or anything like that. These all have to be in the standard units. And then the last thing I want to talk about is modeling this. So if I have a negative charge and a positive charge, if you think about it, negative times positive gives you a negative. And they're unlike charges, and they like to attract. So modeling with signs here. The sign of the force gives you the attraction or repulsion. So the sign of the electric force or you can just think about it conceptually. If they're unlike, then this thing will be attracting, and if they're alike, they will be repelling. And if you notice, that's true too. Even if I have two negatives, right? If I do negative times negative, that actually is positive. So this models repulsion too. So everything works out mathematically. So when it comes to modeling the forces between the two of them, if I ask you to sketch this, it's going to look like this. In other words, that the force from object B is going to be the same from object A, whether it's repulsion like this one or attraction like this. The forces between each other are the same. It's crazy. And this is even true for unlike charges. It's so weird to think that, you know, if I have a positive Q here, but say I have a 4 times as strong positive charge, the force between them are still the same. This is Newton's third law. This is what it means. Force is same regardless of size of charge. Crazy, I know. It's hard to think that this thing is not pushing as much as this. But this is physics. This is how physics works. Trying to be dramatic there. I don't think it worked out. That's okay. Okay, so I'll tell you this. Your calculations will be plug and chug. I'll give you all but one to worry about, but it's still important to kind of see how we go through these types of calculations when we do it. So Athena rubs 2 latex balloons against her hair, causing them to become negatively charged with that amount of charge. She holds them at a distance of that apart. What's the electric force between the balloons? Is this attracted or repelling? So we have a balloon. Terribly drawn. Try again. That's what I meant to do. The balloon is negative. It says that, causing the balloon become negatively charged. And this says balloon, so they're both negatively charged. And they both have the same charge, 2 times 10 to negative 6 coulombs. And then the distance between these two charges, she holds them at a distance of 0.7 meters apart. Just like that. Okay. As always, drawing a picture is incredibly helpful in terms of visualization and what's happening here. So, let's take a look here. My charges are in coulombs, so that's good. My distance is in meters, that's good. And actually, that's all I need to solve this. This is just a constant. So the electric force is going to be K Q times Q. Now, if you want to shortcut this, you could just square this, not double, because it's multiplied. We're squaring this. So you could do that. If you're like, I'm just going to square it. Most common mistake is this here, forgetting that squared. So be careful with that. All right, I'm going to go ahead and calculate this. So 8.99 e to the 9th times 2 e to the negative 6 times 2 e to the negative 6 divided by 0.7 squared. I almost forgot. Told you. It's very tricky. Force electric is going to be 0.0734 newtons of force between the balloons. Now, I did technically forget something. These should be negative. But if they're negative, and they're both negative, they're going to repel each other. So usually I actually don't put the negative signs into later, but if you want to be consistent, this would be correct. And these would feel the same force of 0.0734 newtons, both of them. That's what this number represents here. That's the force between them. So it's a small force. It's not huge, but it's enough to be pushed apart. And mathematically, you'll notice that this does come out positive, which does represent repulsion. So that's another way you can kind of confirm this kind of question. All right, questions on this? You can ask questions. I'm so used to saying that. Sorry. If you have questions, let me know. Hopefully that was pretty straightforward. So I do this in class. This is a quick example. Like imagine if I was holding 2 protons. The calculation is incredibly small. You can see it's the force is to negative 28. If I were to physically hold 2 protons at like this far apart. So pretty much what would happen if I were to do that, they'd probably just sit there because the force between them is so strong that the force wouldn't even actually exist. You wouldn't see them being repelled because the force would just be too small. So just a consideration of how small that force is. Let's do another calculated question. I just lost my pen here. So another way I can present a question for you. So each of the 2 hot air balloons requires a charge of this on its surface and travels through the air. So fun fact, they don't always have to be the same charges. By the way, these questions just happen to be the same charges, but that's not always true, so just know that. Okay, stop. So, there we go. Okay. How far apart are the balloons? So, I have 2 hot air balloons. There we go. There we go. Lovely. Another one. 2 hot air balloons. There they are. Each of the 2 hot air balloons requires that much charge, so it's the same amount of positive charge. Already in coulombs, very good. I'm not so nice in the homework, so just be aware of those. The force between them, so they're the same charge, so they're going to be repelling each other. The force between them is 8.1 times 10 to the negative 2 newtons of charge. The question is, how far apart are they? What's the R? How far apart? So, here's our equation. The electric force is Q1, Q2 over R squared. I'm going to go ahead and apply the following information. So notice that I put the both forces here. That's the force they're being pulled apart, but you just need one of them here. You don't need both. This is the same for both. K is our constant. Coulomb squared, sorry. I am going to square it now because they're the same numbers. It's positive, and we can just square them since they're the same. All divided by r squared. Now, remember, you could do that trick. You could flip those two as long as the variable is on the bottom like that. So r squared is going to be 8.99 times 10 to the 9th. I'm going to skip units just to be quick here. Bad teacher. All divided by our force. Now, technically, this is squared, so I have to square root it. So, in terms of how you want to do this or set it up, it doesn't matter. I'm just going to leave it like that and just do this first. So, 8.99e to the 9th times 3e to the 5th divided by 8.1 e to negative 2. So I get a pretty big number here. Yeah. Okay, I'm going to redo my calculation because I made an error. So that's why it's always good to check your work. And I know where I made my error because that should be negative 5, which is fine. I'll fix that in a second. That's way better. So this should be negative, just FYI. So I get 3.2963. This becomes meters squared. You can believe me that the units work out, or you can ask me via email and I'll be happy to demonstrate that. There we go. There we go. That makes sense. About 1,800 meters apart of two hot air balloons. That makes total sense. I'm going to put it on this. It's going to be on a sunny day. I think it's going to be a nice early morning with some clouds in here. That'll be good. Just like that. Could use some sun today. Nice cloud. Look how nice that is. So yeah, about, what do we say? About 1,824 meters apart. I colored my hot air balloon. Because this makes me happy, okay? I need some happiness. I'm not unhappy, but, you know. This makes me happy, the little things. There we go. Yeah, looks good. Awesome notes. Anyway, that's how you calculate the R when it comes down to that. Okay, now we're going to shift gears from calculations and we're going to predict the value of forces. Now, this is pretty tough. This is one of those things you're going to have to watch a couple times maybe or ask me questions about. You will have this on your quiz, so, you know, just FYI on that. So this is what's happening. So we're saying this charge and this charge. Now notice there are 4, if I can count, 1, 2, 3. The original force is 4 blocks, and they're both positive Q's, so they're just one value of Q. So the original force is the size of 2 arrows. Notice that, right? 2 arrows. So anytime I have 4 blocks in between and 2 charges, it's going to give a force of this much. So the question is, what if I change this one to 2Q instead? I have twice as much force now. I hope that makes sense. If you look at the equation, if I do force is equal to 2Q, and 4 blocks equals D, we'll do that. Q over D squared. This is the same as the original, which was the Q and Q over D squared, but now I have a factor of 2, which means this force has to be doubled. Or if this like totally threw you off, think about it conceptually. If I double the force, it's directly proportional. If I double the charge, then I'll double the force. In order to show this graphically, I'd have to make this not 2, but 4 blocks long, because I just doubled the force. This is F. This is 2F. And they're going apart, because they're repulsive, like that. So I want you to predict the value of force if I change either the distance or the amount of charge. So take a look at here. It's the same scenario, but now one of them is negative. So we're going to have twice as much force because I have extra charge by 2. But now they're going to go inward, right? So this one's going to be attracted to this by 4 blocks. 1, 2, 3, 4 to represent 2F. And this is 1, 2, 3, 4, 2F. Like that. So the way to think about this, I'm going to give you, if the force is directly proportional to charge. So if it's 2Q, then it's 2F. If it's 3Q, then it's 3F. If it's 4Q, then it's 4F. But it's inversely square proportional to the distance. So if the distance widens by a factor of 2, then it decreases by a factor of 1 over 4, which is what I explained earlier. So let's take a look here. Here's a bunch of them. This is challenging. I would make you do this in class to try it out, but please try this out. Pause the video, work these through, get answers, because it's always good to change your answers and practice the thinking versus just waiting for answers and then relying on me thinking, because that's not what's going to get you through the exam. You need to practice thinking. So pause the video and try these out. Okay, I'm going to assume that you paused the video and tried them out. So let's go ahead. So I hope you notice that this one is the same as the other one. It's twice the amount of force, and they're attractive, and it just switched 2 to 2. It doesn't matter which one's doing it. And the other thing, if you hope you notice, is that because of Newton's third law, these are always the same. Not just because this one's stronger doesn't mean that this is stronger, okay? Notice that this is wrong. I'm going to show you. This is wrong. This is wrong. This is wrong. The force has to be the same between charges. So the lengths will always be the same. So even if you get the lengths wrong, at least they'll be the same. You'll get credit for that. All right, now we're going to do this for realsies. Okay. Fun. 2 and 2 is 4 times as much. But now, no, they're attracted. So 4 times as much would be 8 blocks, right? Because the original was 4 blocks. Equals F. Oh no, it was 2. It was 2. That was the original one. So if I do this times 4, that means 8 blocks. 1, 2, 3, 4, 5, 6, 7, 8. And it's the same between this one. 1, 2, 3, 4, 5, 6, 7, 8. I think I counted right. This is 4F and 4F. Okay. So that's the answer to that one. Now these are attracting because of the opposite signs. But now we have distance in our account. So let's see. We have 1, 2, 3, 4, 5, 6, 7, 8. They're 8 apart. We had 4 blocks for distance. That's what it was. But now we have 8 blocks. The original was 4. If I do 8 divided by 4, it's a factor of 2. So distance, so if I double the distance, remember, and we square it, it becomes 4d squared. Or in other words, that this is going to be reduced by 4 from distance. But increased by 2 from charge. So that's fun, right? So what that means is, for E here, the force is going to be 2q over 4d squared, right? Because we already did that. So if I just take out the factors, I get 2 over 4 q d. So the force is now reduced to 1/2. Oops, I don't want to load gallery. Got it? No. So this is now reduced to 1/2. So it would be 1 block, because the original was 2, like this. So essentially it means that the further apart you are, it means a weaker force. Hopefully that makes sense. And the weaker force is decreased not only by 4, but it did have a factor of 2 to increase it. If I do F and do the same kind of thing, I get 2q for the first one. I mean, technically one of them is negative. I get 2q for the second one. And then it's 2 squared again because we have a factor of d. So this becomes 4q over 4d squared. 4 over 4 is equal to 1. So in fact, this is attracted with the same amount that we originally started with. So the force here is just F with 2 blocks, like that. So ultimately, what this means is that both the size of the charge and the distance changes the amount of force. The effect of the force is greater in distance. Notice how much it changes it, right? We kept the distance the same for most of them, and we could see how much the force increases and decreases based on just charge, right? 2 versus 4. But then the force is significantly reduced when it's further away like this. So there's some more you can try, or try this again later. Some more predictions. So imagine you have charges like this, right? Now it's asking us to predict the force on charge C. So we have to pay attention because it wants it on this. So when I predict the force, I use 2 colors. So let's use A as blue and B as green. So let's go ahead. B is going to repel C. So B is going to push this away at some force. Now it's going to push away. So it's going to push toward the right. A is also going to repel, but since it's further away, it's going to be a little smaller, right? But if I combine these 2 forces, they both point to the right. If C were able to move, it will go right. Let's keep going. C is now negative. B is going to attract this, so it's going to go this way. A is also going to attract, but less because it's further away. They both point to the left. C will go to the left. You'll get this. C is positive, B is negative. B is going to attract C. But A will repel C because it's the same charge, but not as much because it's further away. B is bigger than A. This will go left. Now, it won't go as much as these because there's a little opposing force, but B is bigger. Last one. C is negative, B is negative. It's going to be repelled, but attracted by A. The direction is right. And there you have it. I want you to be able to predict where the charge goes based on their distance and their sign. You can do this whole thing again with B instead. Changes the question. I could do A. I'm only going to do the first one of B and then move on. So let's make C red and this A. So B is going to be pushed away by A. Actually, since it's close, it's going to be strong. And it's also going to be pushed away by C because they're like charges. But since A is bigger than C, then the answer is right. I lied. I'll go ahead and do these. B is going to be pushed away from A. I just didn't follow my question, right? This was supposed to be C. C was supposed to be, sorry, red. C, okay. C is going to attract, B is going to attract C, but it's going to be small. And A is going to push B, which is going to be big. This is right. B is going to attract C, but small. I am pushing the color, it's just not doing it. A is going to attract B, but big. Left. A is going to attract B, big. C is going to repel B, small. Left. And there you go. Last one. So in this part, what you're going to do is I'm going to ask you to focus on one of these and you have to predict the direction. So what is the direction of the force on charge A? So charge A is this one. B is going to push A in a straight line in this direction. So B is going to push A this way because it's being repelled. A is going to be attracted to C this way. So being pushed down and to the left and to the right, my prediction is somewhere in the middle. This is the net force. On A. And then same thing, what's this one? I could pick any of these charges. So let's see. This one's going to be attracted to this blue one here. I'll call this charge 1 and 2 because they don't have labels. And this one's going to be repelled. It just happened to be the same direction. But now this one's going to be to the left and like this, so it's going to be like this. That would be the net force. Just to show you something different, let me do this one up here. It's not what the question said, but I'm going to do it anyway. This one will push this away, and this one will attract. So the net force would probably be this one. Okay, so this one's smaller than this one. This one's bigger. So we're going to get more of a push up. So it's going to be a slight up versus down, and that would be the force like that. So I'm going to have multiple choice answers, which kind of gives you an idea what to pick so you don't have to actually physically draw these. But you'll definitely have multiple choice where I'm going to ask you, you know, what's the arrow direction that best fits the scenario that you have there. Okay, and that's it for Coulombs Law. So you should be able to do some simple calculations. You should be able to predict the size of the force given an example. You have to have an example. I can't just ask you to do this. And in fact, I won't even change the example, but I could change any of these numbers. And then be able to identify the size of the forces and multiple forces on different charge distributions like this. And that will conclude our video for Coulombs Law. If you have any questions, let me know. That's what Wednesdays are for, and or just send me some emails. Have a good one.